In this video, we'll solve our simple example in LibreOffice. Open the spreadsheet IMRT SimpleExample.ods. At the top of the spreadsheet is our data. It gives the dose at unit intensity of each beamlet to each voxel. The beamlets are the 6 rows, and each column is each voxel. So we saw in the previous video that voxel 1 gets a dose from beamlets 1 and 4, voxel 2 gets a dose from beamlets 1 and 5, etc. We have a column for each voxel up to voxel 9. Below the data, we have our decision variables, which remember are the intensities of the beamlets. So for each of the 6 beamlets, we'll have a decision variable. These are marked in yellow. They're empty for now because these values will be filled in by the solver. Below the decision variables, we have a spot for our objective. Our objective is to minimize the total dose to healthy tissue. The healthy tissue voxels are voxels 1, 3, 4, 5, and 9. Let's go ahead and fill in our objective cell. So we want our objective to be the sum of the dose beamlet 1 gives to voxel 1, plus the dose beamlet 2 gives to voxel 1, plus the dose beamlet 3 gives to voxel 1, etc. We can do this more efficiently using the sum product function that we used in the last lecture. So go ahead and type in the objective cell equals sum product, and we want to select all of our decision variables, semicolon, and then scroll up and select the 6 voxel 1 cells. So what this does is it will multiply the first decision variable by the first dose to voxel 1 plus the second decision variable times the second dose in voxel 1's column, etc. So we want to do this for all of the healthy tissue voxels. So that was for the first voxel, so we want to do this again for the third voxel. So sum product, select all of the decision variables, and then select voxel 3's 6 values. And now do this again, but this time for voxel 4. So select all of the decision variables, and then the voxel 4 column, and again for voxel 5, the spinal cord. So sum product, all of the decision variables, semicolon, the 6 voxel 5 values, plus lastly, we want to do this for voxel 9. So sum product, select the 6 decision variables, semicolon, and then scroll over to select the 6 values for voxel 9, and hit enter. You see right now our objective has value 0 because all of our decision variables currently have value 0. Below our objective, we have our constraints. The first 4 constraints are for the tumor. Each tumor voxel needs a minimum dose of 7. So for the left-hand side, we're again going to do sum product between our decision variables and the dose values for each of the tumor voxels. So for the first constraint, the left-hand side will be sum product, select all of the decision variables, semicolon, and then scroll up and select the dose values for voxel 2, our first tumor voxel, and hit enter. That value needs to be greater than or equal to 7. Now for the second tumor voxel, voxel 6. Again, the left-hand side is sum product, and then select the decision variables, semicolon, and then we'll scroll up and select the dose values for voxel 6. This constraint also needs to be greater than or equal to 7. Now for voxel 7, the third tumor voxel. The left-hand side is equal to sum product, the decision variables, semicolon, and then the dose values for voxel 7. Again, this needs to be greater than or equal to 7. And lastly, for our last tumor voxel constraint, This one's for voxel 8. So sum product, select all of the decision variables, semicolon, and then scroll up to select the doses to voxel 8. And hit enter. Again, this one should also be greater than or equal to 7. Our last constraint is for the spinal cord. The total dose to the spinal cord should be less than or equal to 15. So on the left-hand side, we have the sum product of our decision variables and the doses to voxel 5, which is the spinal cord voxel. This needs to be less than or equal to 15. Now we're ready to solve our optimization problem using the solver. So go up to the Tools menu and select Solver. A window should pop up where we'll define our problem. The target cell should be the objective cell, so put the cursor in the target cell box and click on the blue objective cell box. We want this to be minimized since we're minimizing the total dose to healthy tissue. In the By Changing Cells box, go ahead and select the 6 decision variable boxes, the ones highlighted in yellow. Then we define our constraints down in the Limiting Conditions area. Since our first 4 constraints are all greater than or equal to constraints, we can put them into the solver together. So on the first left-hand side cell reference box, go ahead and select the 4 left-hand sides for the first 4 constraints. The sign here, or the operator, should be greater than or equal to, and the value should be the 4 right-hand side values. Next, go ahead and define the last constraint. So the cell reference should be the left-hand side for the spinal cord constraint, which should be less than or equal to the right-hand side for the spinal cord constraint. Lastly, we want to make sure that all of our decision variables, so select the 6 decision variables, and change the operator to greater than or equal to, because we want them all to be greater than or equal to 0, or non-negative. The last thing you want to make sure to do is go ahead and click on Options, and make sure that the solver engine being used is the linear solver, and hit OK. Now just click on Solve. The solving result says, Solving successfully finished, result 48.5. Go ahead and click on Keep Result. You can see here now that our decision variables have all been filled in with values. The intensity for beamlets 1, 2, 3, and 5 are all greater than or equal to 0. Our objective value is 48.5, which is the total dose to healthy tissue, and we can double check that each of the tumor voxels is receiving a dose of at least 7, and the spinal cord is receiving a dose of no more than 15. In the next video, we'll see an example of a full problem and how big the scale is when solving this on an actual tumor case.